Hello everyone, continuing with the carbon family, in this video I will tell you some important compounds of silicon. Okay, so the heading is compounds of silicon. The compounds which we are gonna see in this video are the following. We would see silicon dioxide. Okay, SiO2. Okay, silicon dioxide because there are two oxygens. Then we are gonna see silicates. Okay, finally we would see silicons. Okay, so starting with the first compound, that is silicon dioxide. Let's start with silicon dioxide. Okay, the first fact about silicon dioxide is that silicon dioxide is also called silica. Okay, it is also known as silica. Okay, silicon dioxide is covalent. Okay, and the structure of silicon dioxide is a three-dimensional network. Okay, it is a three-dimensional network. Okay, it has a three-dimensional network with each silicon atom bonded with 4 oxygen atom in tetrahedral manner. Okay, so each silicon atom is bonded with 4 oxygen atoms in tetrahedral manner. Okay, and each oxygen atom is bonded with another silicon atom each oxygen atom is bonded with another silicon atom, and the corners of the tetrahedron are shared. Okay, okay, so this was the text. Let me explain you by drawing the structure. Okay, the structure is somewhat like this. We have silicon over here, Si. It is bonded with oxygen, oxygen, oxygen and oxygen. This is the tetrahedral bonding. Okay, you can see the tetrahedral bonding, like this would form a tetrahedron. Okay, this would be a silicon would be the top of the pyramid and oxygen would form the base of the pyramid. Okay, now consider this, that there is another oxygen, there is another silicon dioxide, or this pyramidal structure is repeated. There would be silicon over here. Okay, there would be oxygen over here, oxygen would be over here, one oxygen would be over here, and this oxygen, it would be shared. Okay, this oxygen would be shared by this silicon, this entire structure. Okay, and you can again see that this again forms a pyramid. This would be another second pyramid. Okay, and similarly the other oxygens, like the corner of the pyramids which are formed by the oxygen, are shared by other pyramids. Okay, so basically this is the structure of silicon dioxide. Okay, silicon dioxide is very unreactive in nature. Okay, it has a very strong silicon oxygen bond enthalpy. Okay, it has very high SiO bond enthalpy. Okay, the bond enthalpy of silicon oxygen is very high, so it is non-reactive. So it is non-reactive. Mostly, basically it does not react with most of the compounds. Okay, so this was all about silicon dioxide. The next compound which you would see is silicates. Okay, so we are gonna see now silicates. Now silicates are a bit important and you need to take care of these. Okay, these compounds are important, some of the important compounds of silicon. Okay, now silicates, there are several types of silicates. Okay, we are gonna see the type of silicates one by one. Okay, so first of all, which you would see is the first type of silicate which you would see is called the orthosilicates. Okay, the first type would be orthosilicates. Now, what are orthosilicates? The structure of orthosilicates is like this. There is a silicon over here, there is oxygen, there is oxygen, and oxygen, and there is a 4- charge. Why? Because valency of oxygen is not satisfied and each oxygen contains 1 electrons. Okay, so this is the structure. So basically the formula for this is SiO4 4-. Okay, and you can also draw this structure in this way. Okay, generally the structure of this is drawn like this. There is oxygen, there is oxygen, there is oxygen. Okay, like this. Then there is one more oxygen over here. You draw like this. So what does this symbolizes? And in the center you put a dot. Okay, now let me tell you what does this symbolizes. The O here symbolizes that it is the oxygen atom. Okay, and the dot, okay, the dot which I have drawn over here is, this symbolizes the silicon atom. Okay, so basically this structure is used to represent orthosilicates. Okay, and further silicates we will represent by following this structure itself. Okay, so basically it is that the silicon is at the top. Okay, there is oxygen below it. Okay, and we say that the 3 oxygen are bounded to it. Okay, and each oxygen would have a minus charge. Okay, each oxygen has a minus charge. Okay, so this is the structure of orthosilicates. The next type of silicates is the pyrosilicates. Okay, so the pyrosilicates, the structure is as follows. Again, we will draw oxygen over here, oxygen over here, oxygen. Okay. Now, the only difference between pyro and ortho is that one of the oxygen of the ortho is shared by another similar structure or another orthosilicates. Okay, when one of the oxygen of orthosilicates, when one of the oxygen of orthosilicates is shared by another orthosilicates, then it forms pyrosilicates. Okay, so this oxygen is shared. Okay, and there is silicon over here. Okay, and where would be the minus charges? Can you guess? That minus charge would be present over here, here, and here, and here, and here. There would not be a minus charge present over here. Why? Because this oxygen is shared by this oxygen is shared by this silicon and this silicon. Okay, so there won't be a minus charge over there. Okay, so the important point over here is that 2 tetrahedral units are joined. okay, by sharing oxygen at one corner. Okay, so basically two tetrahedral units, that this is, see, this was a tetrahedral unit, so the point was that we shared this oxygen. Okay, so two tetrahedral units when share an oxygen, then pyrosilicate is formed. Okay, so the next type of silicates which we will see is, and just one more thing, and the minus charge is present with the oxygen, which is bound to just one silicon atom. Okay, so let me write this down. Minus charge is present on oxygen that is bound with one silicon. If it is bound with two silicons, like this oxygen is bound with two silicons, then it won't have a minus charge. Okay, so the next silicate which you would see are called the cyclic silicates. Okay, so now each tetrahedral unit is used to form cycles. Okay, the structure is something like this. There are two common well-known compounds. The compounds are Si3O9 6- and Si6O18 12-. These are two well-known cyclic silicates. The structure of these are as follows. Okay, the first compound, it looks something like this. Okay, okay, and there are silicon present over here. Okay, so here and here you will have silicon, and rest all the rounds are oxygen. Okay, and minus charges would be present to all those oxygen which are not bound to silicon. This is bound to just one silicon. This is bound to just one silicon. This is also bound to just one silicon. This is also bound to just one silicon. But this oxygen is bound to this and this silicon, so it won't have a minus charge. Okay, again, this oxygen is bound to just one silicon, so it will have a minus charge. This also will have a minus charge. This and this again won't have a minus charge because they are bound to this, this silicon and this silicon. Okay, so they won't have a minus charge. Okay, so hope you have understood that. The next structure of this Si6O18 12- is something like this. Okay, this is a hexagonal ring, and the oxygen atoms are like this. Okay, and the silicon atoms are present. There would be more oxygen atoms over here. In the center, and silicon atoms would be present just on top of them. Okay, and minus charges would be present where? On those oxygen atoms which are bonded with just one silicon atom, like these. These are bonded with just one silicon atom, and these are also bonded with just one silicon atom. But against other oxygens like this oxygen, okay, or this oxygen, all these oxygens are bonded with two silicon atoms. See, one over here and one over here, so they won't have negative charge. Okay, so this was the structure of cyclic silicates. Okay, now there are one more form of silicate, that is called the chain silicates. Okay, these are the chain silicates. Okay, chain silicates are further classified into two types. The first type is of a simple chain, and the next type is a double chain. Okay, the example of simple chain molecules are like this. The structure is like this. Okay, so this will form a simple chain, and the silicon atoms would be present over here. The negative charges would be present where? The negative charges would be present over here. Negative charge won't be present over here. Let me tell you why. Because this structure is continued. This chain is continued. So this oxygen would be linked with another tetrahedral atom. Okay, something like this. So there won't be negative charge over here, and there won't be negative charge over here. And negative charge would be over here. Okay, so this will form a chain silicate. Okay, and this would be a simple chain. Now, the feature about this simple chain is that two corners of each tetrahedron, okay, are shared. That's all. So two corners of each tetrahedron are shared, and thus they form a long chain. Okay. Now the next is the double chain silicates. Okay. Next would be double chain silicates. Okay, double chain silicates are very similar to single chain or the simple chain silicates. Okay, the structure is as follows. First you draw the simple chain silicate. Okay, you draw a simple chain silicate. Okay, you draw one simple chain silicate. Okay, and the atoms would be present over here, silicon atoms. You have drawn one simple chain silicate. Now what you do is that you join one simple chain silicate with another simple chain silicate. Okay, so what you do that you join them. So join would occur from this point. Okay, like this. Similarly, like this. Similarly over here. And like this. Okay, so you can see now that this is again a simple chain. This is again a simple chain silicate. This part. Okay, so this entire part is also simple chain, and this entire part is also simple chain. Okay, both are simple chain silicates, and you have joined them in between. Okay, with these atoms. You have joined them with these oxygen atoms. Okay, and the negative charges would be present over. Where would the negative charges present? They would be present over here, 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 and here. Because all other oxygen atoms would be joined. All the oxygen atoms are joined with another tetrahedral ring. So they would be shared by two silicon atoms. Okay. So the important feature about this is that this is joining of two simple chain silicates. Okay. Each corner is shared. Okay. Each corner of tetrahedron. Okay. Each corner of tetrahedron is shared. Okay. So this is an important feature. Okay. With this we are over with silicates, and the next silicon compound which we are gonna see is silicones. Okay, so the next and the third compound is silicones. Okay, now silicons, they are basically, the important feature is that these compounds are held by compounds have repeated R2 SiO units held together by SiO-Si linkage. Okay, so this is the important feature, that they have repeated R2, where R stands for this R, it stands for any alkyl group like CH3, C2H5, etc. Okay, it can be any and other. Okay, so it can be anything. Now how do we get this silicones? How do we prepare them? Okay, so they are generally prepared by hydrolysis. Okay, their method of preparation is generally hydrolysis. Okay, let's see. Their method of preparation is hydrolysis. Okay, so first we would see the hydrolysis of R3SiCl. Okay, so first we would see hydrolysis of R3SiCl. So what will happen? Suppose we have this CH3SiCl. Okay, when we pass water through it, we get CH3SiOH. This is CH3 whole 3 and this is also CH3 whole 3. Okay, so chlorine is removed and we get CH3SiOH. Okay, now this CH3SiOH, the structure would be something like this: CH3, CH3, CH3. When it reacts with another molecule of CH3 SiOH, CH3O3 SiOH. Okay, and when you remove water from this, okay, minus H2O, then what will happen? Then you will get what? You will get this CH3Si, CH3, CH3, O, Si, CH3, CH3 and CH3. Okay, so you can very well see this SiO-Si linkage. Okay, SiO-Si linkage is formed and therefore this is a silicon. Okay, now the next which we would see is the second, by hydrolysis of mixture of CH3O3 SiCl and CH3O2 SiCl2. Now we will do hydrolysis of this mixture. Okay, so when we hydrolyze this mixture again, similar to this, we would do the hydrolysis, and what will happen? This compound, okay, this will form the Ci would be replaced by OH. Okay, Ci would be replaced by OH. Here also Ci is replaced by OH, but there would be OH whole 2. Okay, so this forms the middle compound, okay, or the middle element, and this forms the end. A chain would be formed, and which would look something like this. The terminal would be Si, CH3, 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 O. Then there would be, SiO, again Si, CH3, CH3 and CH3, and this entire part would be repeated. Okay, there is CH3 over here and over here. So basically what I mean to say you is that, see, this compound, okay, this CH3 whole 2 forms the center part, okay, this part, it forms this, and this forms the terminal part or the chain ending part. Okay, and again there is SiO-Si linkage, and therefore it is a silicon. Okay, now you can also get the two-dimensional cross-linked polymer also. Okay, the third would be the third form or the third type of structure of silicons would be this. It would look something like this. Okay, it would be a two-dimensional polymer in which there would be SiO, dot, SiO, here there would be Me, Si, Me, O, here also it would be a dot, then there would be this. Again, this O would be linked with Si. Again, this O would be linked with Si, and these individual Si would be linked with O's. Okay. Again, there would be Me over here, Me over here, Me over here, and there would be O, and there would be dot. So you can see the two-dimensional structure, and this is a cross-linked polymer. Okay. This is a cross-linked polymer. Okay, and its chain can go in the two directions. Okay, both the directions can form a sheet, entire sheet. Okay, now the important point about silicons is that, let's see some important points. They are chemically inert. They are water repelling. Okay, they have high heat resistance, okay, and they are also good electrical insulators. Okay, because of these features, silicones have a wide range of applications. They are used for making wires, okay, and other compounds, other day-to-day uses, rubbers, etc. Okay, so with this we are over with the compounds of silicon. In the next video, I am going to tell you about the compounds of tin.